Welcome, everyone. Antoine's going to be talking about the cohomological variety of a vertex operator algebra. Feel free to start whenever you're ready.
Yeah, so thank you very much for the opportunity to talk here today. So I'll talk about a joint work with Tupo Zhang from Shanghai Jiao Tong University and Zhongju Lin from Kansas State University. So first, briefly a plan of the presentation. First, I will give some motivation as to why we are interested in this subject and what we want to achieve by introducing this subject. Then I will give some definition on how to construct the main object, this cohomological variety, and some of its properties, what we found on the internal structure of this object. Then the two main parts will be parts 3 and 4, where I will first give a construction on how to obtain information on this object, because the definition is a little involved, and at first you don't see how to get information on this. And finally, I will give example on how to apply this construction to two main examples, namely the Virasoro vertex algebra and the simple affine vertex operator algebra. So first, motivation. In vertex algebra, we can see them as analogs of both ring and Lie algebras. So this is the algebraic point of view. And if we want to take a geometric point of view on vertex algebra, usually it goes through the associated variety, which is the maximal spectrum of the C2 algebra. There are important information contained in this variety on V itself that I will mention later on. So this is work mainly done by Arakawa. And the idea is, what about the cohomology of this space? Instead of looking at the algebra directly, look at the cohomological side of it. What kind of information on V could we recover? So this is one motivation. The more general perspective on this would be to develop a theory of cohomological support variety for vertex algebra modules. So there are already things done for finite groups in positive characteristics. So this was done by Carlson, and also for finite dimensional algebra using Hochschild cohomology rings. So they are analog in different domains of those cohomological support variety. The idea would be to bring those notions to the vertex operator algebra representation. So some preliminary notions before I can give the definition. So if you have a vertex algebra V, you can define the space C2 spanned by all the, let's say, -2 products in your vertex algebra. And then if you quotient V by your C2, so it's called the C2 algebra. And as such, it is a commutative associative Poisson algebra with a unit. So the product is given by the -1 mode. The Poisson structure is given by the 0 mode, and the unit is just the image of the vacuum vector. And furthermore, if V is a vertex operator algebra, so you have a gradation given by the conformal vector, this gradation is transferred to the C2 algebra, and then you get a graded Poisson algebra. So as I mentioned in the brief introduction, the associated variety is the geometric version of V. And so it has some interesting properties that you can read on the geometrical side to get details on the algebraic side. So for example, with some minor assumptions that I won't mention here, there is an equivalence between the dimension of V being 0 and the C2 algebra being finite dimensional, so the VOA being C2 cofinite. And a very interesting also property is that if we call, so LG of K is the simple vertex algebra constructed on the simple finite dimensional Lie algebra G. So the L means the simple one. So if you look at the associated variety of this simple vertex algebra, it's going to be the closure of some orbits in the nilpotent cone of the Lie algebra itself. for only admissible level. If K is not admissible, you have other characterization. But the idea is to get algebraic information from a geometric characterization. So we want to do just that, but for, I mentioned the cohomology of RV. So what do we mean by cohomology? Because the word can mean a lot of things depending on who you're talking to. So to set the stage, we will work with an n-graded VOA, so no strictly negative weights. And so, as I mentioned before, the C2 algebra is going to be an n-graded algebra. Here, and in the rest of the talk, the Poisson structure, the Poisson structure, we won't care for the Poisson structure. We only care for the algebra and the gradation on this algebra. So if you take a maximal ideal in RV0, RV0 is a subalgebra of RV. So you take a maximal ideal and you look at C index X to be this quotient. So it's an RV0 module, and by the projection from RV to RV0, it's also an RV module. And the idea will be to study this object, so HX. So to constrain the notation, it will be the X algebra or Yoneda algebra for RV for the module CX. So this is called in literature either X algebra or Yoneda algebra, depending on the author. So what is going to be this space if you're not familiar with it? So there are two ways to look at it. They are both equivalent definitions. The first is a more, let's say, constructive approach. Is you take a projective resolution of your RV module CX, any projective resolution, and then this X algebra is going to be the cohomology of the cochain complex obtained in this way. So you take the morphisms, the RV morphisms from the projective resolution to CX. Your projective resolution is a complex. You take hom, it gives you a cochain complex, and then the cohomology will give you your space, and it will be independent of the resolution. The other more, let's say, you can see better what are the elements of your space. You can see them as equivalence classes of exact sequence of RV module, which will start and end at CX. So because we have CX here, we have CX here, CX here, meaning that the sequence will start and end at CX. So something that we cannot really see from description 1, but which become more apparent in description 2, is that, as I mentioned, it's an algebra, so there is a product, and this product is given by the splicing of exact sequences. So if you have this sequence here and the product with this sequence here, you just construct this diagram, and this composition, you define the map here to be the composition.
Okay, sorry to interrupt a little bit. I have a question about application. Can you go to previous slide?
Previous slide, yeah.
Yes. Just over here. So you have got RV sub 0 over here. So
yes.
What do you mean by sub? So 0 means the weight 0 is homogeneous subspace, right?
That's right. Yeah.
Okay. So in the case, for example, like VO, so should it be the quotient of the V sub 0?
Yes, it is. Yeah.
So for example, like if like V is actually like of a safety type, so in this case, yeah, the 0 homogeneous vector space is just spanned by the vacuum. In that case, you just like one-dimensional algebra.
Yeah, then it's just the field, and then mx will be just a point. There is no choice.
I see. Okay, yeah, that's my question.
In the examples that we will see, it will be exactly like that. There will be only one
I
choice. It will be the point 0.
Okay, great. Yeah, thank you very much.
You're welcome. So here you have a product, and you also have the Yoneda algebra is going to be graded, where, as you can expect, the space of degree n will be given by the exact sequence of length n. So the short exact sequence will be space of degree 1, and so on. So ideally, to do the analog of the associated variety, we would want to consider the maximal spectrum of this Yoneda algebra. But the main difference with the associated variety is the the commutativity rules on the unit algebra are not as easy. It's not commutative, and it's not even graded commutative either. So we need some type of commutative version of this space to make things work. So we are going to define this upper script ab for abelian to be the biggest commutative quotient of the unit algebra. So there are two ways to think of it. Either you quotient by the ideal given by the commutator. Given by the commutator, or you can see it as the following space. So it will be a subset of the direct product where the notation are given as such. So you consider Ix to be the set of two-sided ideals in your unit algebra, such that the quotient is commutative. So you take the kind of the collection of all the commutative information of your quotients. And for two ideals I and j inside Ix, you have maps phi ij from the quotient that sends the small quotient to a big quotient to the smaller quotient. And this Ix and those maps will define an inverse system, so you can take the inverse limit. So this is the inverse limit description. The interesting aspect of this inverse limit is the inverse limit, let's say, characterization is we come in the next proposition. First, this remark is that in general, if you take any algebra R, this abelian version may not be an interesting object. So for example, if you take the Weil algebra, then this abelian version is just going to be 0. And if you take the enveloping algebra of some simple finite dimensional Lie algebra, you will just get the field that you started with. But here, everything will depend on what the commutation rules are. And for the unit algebra, they are not nice enough so that the product is commutative, but they are still nice enough so that the abelian version of the unit algebra will be close enough to what you started with. So the commutation rules are kind of in between the ideal case and the worst case, which would be, for example, this Weil algebra product. So the definition of the cohomological variety now we can give is the cohomological variety of V at the point X is going to be the maximal spectrum of this abelian version of the unit algebra. So we keep the same notation with X index V, and we keep the point X, and we add a shriek to indicate that we are in the cohomological realm. So it's not just the associated variety. One important thing to notice here is that we have no idea, at least for now, on the finite generation of this commutative ring, commutative algebra. It might be finitely generated or not. So maybe this variety is of finite type or of infinite type, but for now it's completely unspecified. We don't have any information for that right now. We will get more information on that later on. So as I mentioned, the interesting aspect of the description by the inverse limit is that each of your components, if I go back to the inverse limit description here, each of those components will give you a subspace inside your cohomological variety. So if I go back here, so the cohomological variety will be exactly the reunion of the maximal spectrum of all those commutative quotients. So it's not, you might have overlaps in this reunion, but you know that any point in your cohomological variety will be in at least one of those commutative quotients. And so then we can check what are the properties of those of this variety. So we can check that the two operations you can usually work with vertex algebra are direct sum and tensor products. And this behaves well with respect to that. So kind of the direct sum becomes a reunion and the tensor product becomes the direct product, similar to this. And an interesting also property is that with some reasonable assumptions that we will see are satisfied later on, it is impossible to have both the associated variety and the cohomological variety being zero at the same time. So it tells you that if one is kind of crushed to zero, it makes something else pop up in the other realm, either the cohomology or the non-cohomology. But you cannot have both of them being zero at the same time for, let's say, the interesting examples. So now the objective is to find some good commutative quotients. So we'll see what good means later on. But if we find some good commutative quotients, then by taking the spectrum, we will get a subspace of the cohomological variety. So now the goal of the next section is to see how to find such a subspace. So now for the construction, if you consider S to be a commutative Noetherian ring, we need to set up some definitions before I can give the main result. But a sequence of elements in S will be called a regular sequence if, so it's an induction process, C1 is not a zero divisor in S, and then Ci plus 1 is not a zero divisor in S quotiented by all the Ci's that come before. So if you have such a regular sequence, then the quotient of S by this sequence will be called a complete intersection. So something that you might suspect from seeing the definition is that the order is going to be important. So for example, if you look at the polynomial in 3 variables, then the sequence x, y times 1 minus x and z times 1 minus x is going to be regular. There are, at each step, you have no zero divisor. But if you look at this sequence, it's not going to work, because if you quotient this by this one, then this one will be a zero divisor, because this one times y is going to become zero in the quotient. So complete intersection is kind of an odd characterization, because the quotient here doesn't depend on the order of the CIs. But if you want to study the ideal in depth, the order at which you take your successive quotient will matter. So this is an important thing to keep in mind. So if a ring is complete intersection, there is a way to construct a free resolution of a module for this ring. Because remember, the space we want to consider is the Yoneda algebra. And so I mentioned in the two possible ways to see this Yoneda algebra that it can be obtained as the cohomology of, you take the projective resolution of your module, you take the hom of this, and then you take the cohomology, give you your space. So we need a way to construct this resolution. So a construction due to Tate states the following. So if you have two regular sequences, T1 Tn and C1 Ck in your commutative Noetherian ring, such that one ideal will be included in the other, then there is a recipe to construct a free resolution for this module, so C1 over the Ti, for this algebra, S over the C1 Ck. So an important consequence of this construction is that it's going to be finitely generated. So this finite generation comes with a bit of a caveat, is that if you work over, let's say, complex number of field of characteristic 0, you have finite generation as a differential graded algebra. So this works perfectly. If you work over finite fields and the construction still works, you need to include some divided power structure because you have a trick in the construction. So the idea of this construction is you will construct your resolution step by step. So first, you will consider if you have a module, let's say M. Can I write here? Yeah. So if you have your module M, you will consider, and you have a ring R, so you will consider R into M, so the quotient. You see that as a surjection. And then here, you will have, if with this we call it, let's say phi, you will have the kernel of phi here. So you will look at the generator of your kernel of phi, and you will add, let's say, new variables of degree 1. So this will be the space of 0. This will be the space of degree 1. And you will construct a new space, so I, where this is, let's see, can do that like, I cannot erase directly. Yeah. So you add variables ti such that each image of the ti by this map will be a generator of your kernel. And then it will make this part being exact, because then the image of this will be exactly the kernel of this. And then you look at this will add also terms here. And then you look at the part, the kernel for this map here. And you will add parts of degree 2. So you will add generators that will be sent to the generator for the kernel here. And then it will make these parts, this map here being exact. And then you keep going. So the construction works in all generality for Tate, but the issue with the construction is that it may never end. So you might have to make it exact at each step, and it may never stop. So the limit process will be exact, but if you want to compute something, it needs to end at some point. The interesting part of this result is that you know that if something is complete intersection, so if you have regular sequences, this process is going to stop. And so you will add only finitely many of those variables. So that's the important thing to take away from this construction. So if you have some regular sequences like that, you can apply the construction step by step. And from then, we showed that you can find this Yoneda algebra. So for this ring and this module, we have a way to describe it explicitly by generator and relations, depending only on the T's and the C's. So if you have a complete intersection ring S over C1, Ck, then we have a way to construct the Yoneda algebra explicitly by generator and relation. Now, as you might guess, this is the ideal case, but it might not be complete intersection. So if you consider S to be just your polynomial ring in T1, Tn, and this will be the type of ring we will work with. In the ideal situation, it would be a complete intersection, but more often than not, if you take a ring, it's not a complete intersection. So we cannot apply these results, because then, as I mentioned, the construction might go on forever. And you need some type of finite generation to be able to make then computation on it. So what can we do for that? So the strategy is going to be in 5 different points. The first is going to be to add variables to the ring R to construct a new ring R tilde that's going to be a complete intersection, so that we have a surjection pi from R tilde to R. So there is a way to add those variables. So that's why I put cleverly in parentheses, because it's not just random adding of variables. You add them at some places so that it also helps into simplifying the computation afterwards. So you kind of choose the right approach to do it. Then this morphism pi from R tilde to R will induce a morphism pi sharp between the Yoneda algebras, where here the C, we see it as the module R over T1 Tn. So remember, R is the polynomial in T1 Tn quotiented by the relation C1 Ck. So we see the complex field I this trivial R module, and it's also an R tilde module through the morphism pi. Then once you have this morphism, because R tilde is a complete intersection ring by construction, based on the previous slide, we know how to find an explicit description of this Yoneda algebra by generator and relations. So then you can find this description. From there, because you know how this space works, you can compute the image of this morphism pi sharp. And if you have then this space, we can try to determine a commutative quotient of this image. Because if you have that, then you will get a surjection from your Yoneda algebra into commutative algebra. And so because it's a surjection, it will tell you that the space you found is a commutative quotient of your Yoneda algebra, which is precisely what we wanted to do to start with, to find some commutative quotient. So one more definition that I need to introduce is that if you have elements C1, Ck into your polynomial ring, we say that there are minimal generators of the ideal that generates if you take any Ci and it's so it won't be a linear combination with coefficient in your polynomial ring of your Cj. So it basically means that in your generator of your ideal, you have no redundancy in your generator. If you remove one of the Ci's, then you will get a different ideal. Oops, my bad. So the theorem we were able to prove is the following. So if you consider R to be your polynomial ring and your relation C1, Ck, and you assume that C1, Ck are minimal generators, so no redundancy, and they are homogeneous of degree at least 3. So here, when I say homogeneous, we say that T1 and Tn are all of degree 1, so the usual gradation. And we want each of the Ci to be at least of degree 3, homogeneous of at least degree 3. They don't need to be of all the same degree. You might have some degree 3, 4, 5, but you don't allow any degree, so 1, because you will have you could simplify the expression, and you don't allow degree 2. There is a way to work with degree 2, but it's still an ongoing process because computation is much more complicated in this case. So if you have this set up for R, you consider your trivial module R over your variable. Then we were able to prove that there is an inclusion, a closed inclusion, from the affine space of dimension k, where k is the number of your, let's say, minimal relations, into the variety corresponding to the commutative version of your Yoneda algebra. And so, because this is an inclusion in terms just of the prime spectrum, if you look at the maximal spectrum for this, then it tells you that you have a space of dimension k inside the maximal spectrum of this ring. And so if you go back to the vertex algebra, because this is only commutative algebra and then cohomology, there is no vertex algebra involved. But if you find some RV that satisfy this theorem, then it will tell you that you have a space, an affine space of dimension k inside your cohomological variety. And so you get a lower bound on the dimension of your variety. So that's what we are going to apply in an example. Are there any questions on the construction up until now before I go to the examples? Okay, perfect. So first would be the easiest example for the Virasoro vertex algebra. So to set the notation, we say that V index vir is going to be the universal one and L index vir will be the simple quotient. So here we cheat a little because the vertex algebra is, let's say, so small that we don't really need the previous theorem. We can do everything explicitly. And there are known results of what the C2 algebra is. So it's just, for this, the C2 algebra is just the polynomial ring. This one is the polynomial ring. And this one, depending on the value of C, it's going to be either a polynomial ring or a quotient of the polynomial ring by a power of your X. So if you realize the computation, you can prove the following. So for the simple vertex algebra, as Feichi mentioned, for the Virasoro vertex algebra, it is CFT. And so the space of the smallest dimension for the C2 algebra will be of dimension 1. It will be just the field itself. And so if you take a maximal ideal in that, because it's a field, you don't have a choice. So that's why the only possibility is to have 0 here. So for this simple BOA, we have two possibilities. Either C is of the form CPQ, where PQ is not 2, 3, in which case your cohomological variety is going to be just the complex line. Or you are not in this case, and then you just get 0. If you look on the other side to the associated variety, you get kind of exactly the opposite case. So you will get 0 if C equals CPQ, including 2 and 3, and you will get C otherwise. So you kind of see that once, if one is non-zero, then the other becomes 0, and so on. And to compare, we can look also at the universal one. And it will be, the cohomological variety will be 0.
Antoine, one question. This is the CPQs for which the thing is rational. Is that right? So you're thinking of P and Q greater or equal than 2.
Yes, so yes, my bad. So here.
No, that's fine. So C equals 1 would be in the second side of the bracket,
and
right?
Q are bigger than 2, and P and Q are coprime.
Cool. Okay, thanks.
Yeah. Yes, because this P and Q encode the representation theory of the Virasoro algebra. And so it always shows up when you look at the Virasoro vertex algebra. So as I mentioned in the previous section, we proved that you cannot have the cohomological variety and the associated variety being 0 at the same time. And you can see it in this example. If one is non-zero, then the other becomes 0. So you can have both non-zero at the same time. If you do tensor products, then there's no issue. But here you might see that there is a flaw in what I just said, is that you have the PQ equal to 3. And this, we can see it here. For 2, 3, both of them will be 0. So 2, 3 is kind of the, let's say, the degenerate case, because for PQ equal to 3, the C2 algebra of the simple affine vertex algebra is just the field. So it's kind of the extreme case where you just get the field, and then the unit algebra is also the field. So your unit algebra becomes not only commutative, but it's a field. So it's all the, let's say, the complexity and difficulty we had before kind of disappears because you removed everything that makes the situation difficult. So in this case, you will get both of them being 0, but it's kind of the extreme version. If you look at example where the C2 algebra is not trivial, then you will ultimately end up in a situation where the theorem applies and you cannot get both of them being 0 at the same time. So this is kind of the extreme case that you can go to. So now for let's say the more interesting example. So if you start with G,
Antoine, sorry to interrupt. I have a question. What about the associated variety to the non-irreducible Virasoro when the center charge is 0? So 2, 3 corresponds to center charge 0, right?
Yes.
And you said the irreducible one is just trivial in that case. I agree. But what if P and Q are 2, 3, but you have the universal Virasoro?
Then for the universal, it's 0 always, because for the C2 algebra for the universal Virasoro is just the polynomial ring. And so the polynomial ring, if you look at its Yoneda algebra, it's just going to be the exterior algebra with one variable. So it's going to be Cx over x squared. And so for you will get the x for the R of the universal one is going to be Cx over x squared. And then if you look at the Cx, no, it will be just C, my bad. And so then if you look at the maximal spectrum, you will still get 0.
Okay.
Because you have 0, the RV VR is going to be just Cx. So because you have 0 relation, then the Yoneda algebra will be the easiest possible, and the spectrum will just give you 0.
Okay, thank you.
So for now, the affine part, so you take the usual setup where G is some simple and finite dimensional Lie algebra over the complex numbers, and equipped with some non-degenerate invariant symmetric bilinear form, so some proportional to the Killing form. And then, so to fix the notation, if you take any element k as a complex number, you can construct the universal affine vertex operator algebra as some induced module for the trivial module, the trivial one-dimensional module for the positive part of the affine Lie algebra constructed from G. And then we write L for the simple quotient, for the unique maximal ideal. So if you start with this, then we already know that the C2 algebra of this universal VOA is going to be the symmetric algebra of G, where you identify G and G times T to the minus 1 in the affine, in this space. Then, because of this equality here, the C2 algebra of the simple VOA is going to be a quotient of the C2 algebra of the universal VOA by the image of the ideal I into this C2 algebra. So this is what I write with this top bar. So it's the image of the ideal inside the C2 algebra. And this, you can see it as some G module for the action of G. And it will be generated by the E theta to the K plus 1. So this works only if K is a 0 or strictly positive integer, so a natural number. And here also theta is going to be the highest root of G, because it's finite dimensional, so you have a maximal root. So now we have this, let's say, ideal of relation inside the let's say the bigger ring. So if you remember what we said before, this will play the role of the polynomial ring C(T1, Tn), and this plays the role of the ideal of relation generated by C1, Ck. And what we need is information on the number of those minimal relations. How many minimal relations we can give so that we get the ideal of relations. And once we know this number, then we can get information on the cohomological variety. So to do just that, we need information on some presentation of this ideal. So we have we found the following lemma. So you take an integer at least 0 and your G, then you have an isomorphism of graded Poisson algebra. So the Poisson structure here is not necessary, but it just can cherry on top because everything works fine. Between the C2 algebra and the quotient of this symmetric algebra by the ideal generated by all those relations. And the important part, as I mentioned, is going to be how many minimal generator is going to be needed to get this ideal. And this is given by a basis of this space. Because this space, you can see it as a G module, so it's going to be a vector space. And as a vector space, is going to be finite dimensional. And a set of minimal generator of the ideal will be given by this basis, so any basis. And the interesting thing is that because of the structure of this ideal, all those generators are going to be homogeneous and of degree k+1. And so remember that in the main theorem, we needed information on the minimal generator, and we also needed them to be homogeneous of degree at least 3. And so then we can, every time we get a new result, it goes closer and closer to the theorem that we need to apply. So now the question is how to find information on this, on the basis, because we know that the number we want is the dimension of this space. So we can prove that as G modules, this UG applied to E theta to the k+1 is going to be the simple highest weight module of highest weights k+1 times theta. And so when you have through this form, we don't really know what to do with it, but through this form, we have a lot of results. And in particular, we have Weil's character formula. And so if we apply this, we have a direct way to compute it explicitly using the root system of G. So if we write nk for this dimension, it's going to be the following product, where phi plus is going to be the positive part of the root system of G, and rho is the half sum of the positive roots of G. So because phi is finite dimensional, this is the finite product. And so this will give you some polynomial in K, will give you your dimension. So now we have everything we need to apply the theorem, because we needed a ring with some homogeneous minimal generator of degree at least 3. Here we have quotient of commutative ring by some minimal set of generator, homogeneous of degree k+1. So you can see where this is going. We need k+1 to be at least 3. And so when we apply, we will impose k to be at least 2, so that k+1 is at least 3. And then we will get a closed embedding of algebraic variety between a space of dimension n to the k and the cohomological variety of the simple one. So nk, as I mentioned in the previous formula, we can see is going to be a polynomial in k, and the degree is going to be the set, it's going to be the number of roots, positive roots, such that this product is positive. And so it was pointed to us that this is exactly this number. So twice the dual Coxeter number -3. So this can grow very, very fast. For example, I think it's E8, it's 57. So it can grow very, very fast. And so it's an interesting aspect is that depending on what value of K you choose, then you can choose a subspace of dimension arbitrarily large. So if you want some cohomological variety that contains a space of dimension n for any n, it will exist because this K can be as big as you want. So to make the comparison with the universal universal vertex algebra, we know that the C2 algebra is going to be just the symmetric algebra of G. And so, as mentioned before, this is CFT. So there is no choice for the maximal ideal, just the point 0. And then the Yoneda algebra is going to be, at the point 0, is going to be exactly the exterior algebra built on G. And so if you want a commutative quotient, because everything is strictly anti-commutative, the only commutative quotient you get is 0. And so the associated variety for this one is going to be 0. But then it makes sense because we still have this kind of duality. If one is 0, the other is not 0. Because remember here, the associated variety of the universal one is G star. And the associated variety of the simple one is just 0 because it's C2 cofinite. So the associated variety is going to be 0 by Arakawa's result. And so, oops. Yeah, so you did see what I wrote. And so we see that in this example, it also applies that if one is 0, if the C2 algebra, the associated variety is 0, then the cohomological variety is not 0 and vice versa. If one cancels, it kind of forces the information to go somewhere else. So this is an interesting aspect of this result. So something you might wonder is the whole trouble we went through for this construction to get this theorem is to apply the theorem that we mentioned before. And this theorem was based on the fact that the ring you start with is not a complete intersection. So you might wonder, can we improve this bound, this NK, by giving a presentation of this ring that is a complete intersection? So there are two answers. Short answer is no. And the long, more interesting answer is given by this following proposition, is that it's basically impossible to have a complete intersection because it just doesn't exist. So if you stay in the context of K being a positive integer, at least 0, then this spectrum is going to be in G star, and this inclusion is going to be a complete intersection if and only if K is 0, so the kind of degenerate case. So for all the other interesting case where K is non-zero, and so you get this NK as a polynomial in K, you can never get complete intersection. And so if you want information on this cohomological variety, you have to go through this R tilde construction where you approximate your ring, your non-complete intersection ring, by something that is a complete intersection. And you cannot really improve on that. So to finish, I mentioned before that in the definition of the associative variety, there is no mention on the number of generators of this abelian version of the Yoneda algebra. So the question is it even of finite type? So this will depend on the finite generation or not finite generation of this Yoneda algebra, this X algebra. So, and this is a tricky problem because the computation of the Yoneda algebra is very difficult in general case. So for finite group schemes, this is already known. So if instead of RV, you have the group algebra of some finite group over finite fields, then Friedlander-Suslin showed that this is finitely generated. The unit algebra is finitely generated in this case. It's even a Hopf algebra. So this is kind of the perfect case. But for our purpose, we still don't know. There is, when RV is complete intersection, as I mentioned, the Tate resolution ensures that the unida is finitely generated. But if it's not complete intersection, it might go on forever. So I have currently an ongoing project is to look at when is Tate resolution obtained after finitely many steps. So you add finitely many variables. You don't assume that your ring you start with is complete intersection because then you would know it stops. But you assume that Tate resolution stops and then you see what it implies. So it will imply that the unida algebra is finitely generated. And so over it works in all characteristics, but if you have prime characteristic, you need to add some divided power structure coming from Tate's construction. But the odd part is that if it stops after a finite number of steps, then it will necessarily implies that the ring you started with is a complete intersection. So you have kind of an equivalence between a ring being complete intersection and Tate's resolution stopping. So then if you want to compute information on your cohomological variety by using Tate's construction, if you don't have a complete intersection, you need to go through some type of approximation because the Tate's resolution can never be obtained after finitely many steps. So if you want some type of finite generation, you can only obtain it using an approximation. You can never obtain it directly. And so I'll stop here. Thank you.
Thank you, Antoine. If you have questions for Antoine, please feel free to unmute yourself and ask.
So what exactly does this structure tell you about the VOA or its representation theory?
So right now, this we still don't know because we just